Welcome to homework.
Aloha. So in this problem, we are considering the hyperfine interaction in the hydrogen atom. So that's the magnetic in terms of the dipole of the proton and the spin magnetic dipole of the electron. And the electron is split into two different energy states. And something that we're told is the energy between these states shall call delta E, which is 5.9 times 10 to the minus 6 electron volts. So that's something. And we're in the ground state. Two energy levels. And we want to find the wavelength of the light, which I'll call lambda, of the photon that's emitted when the electron goes between these two states. So when it's going from the higher state to the lower state, it'll emit a photon. And we can use the equation for the energy of a photon, which is that E is hc over lambda, where that's Planck's constant and c is the speed of light. So here we want to just flip this around to an equation for the wavelength of the light. And the energy here is the delta E for this energy transition. That's the energy of the photon. That photon is basically carrying away the energy when the electron makes this transition. So then we can just plug in these numbers. So we'll have lambda is 6.626. So you can just look up what the value of Planck's constant in the textbook somewhere. And the speed of light. You want to make sure that you're using consistent units. So since I'm using meters per second for C, I'm using a value for Planck's constant. It's in joules. And because a joule is defined as a kilogram meter per second squared. Now I'm plugging in, that's a 10 to the minus 6 EV. And then we just want to convert this to be consistent with the units of joules in the Planck's constant. Convert the electron volts to joules. So that's the conversion factor there. Let me get rid of the joules and then meters per second. So we'll get an answer in meters for our wavelength. And you should get about 0.209 meters. So approximately 21 centimeters. And you're asked to check this with an example in the book. And this is the same. And this is a radio frequency wave. And the problem part B, the effective magnetic field in these two states. So thinking about the two states of this ground level of the electron being split, and we're looking for the effective magnetic field. So you can find the equation for the energy difference between the states. It depends on the quantum numbers, but the difference between each level will be the Bohr magneton times this effective magnetic field here, and times 2, because really what we're thinking about, and there's a diagram in an example in the book, is that here's the axis for energy, and this is the ground level. So there's like a negative delta E value and a positive delta E value. Here's a 0 value state. So we have basically 2 delta E between these two states. So that's really the energy difference that we're looking for here. And you can just rearrange this equation. And that dipole moment, the Bohr magneton, that's a constant you can find in the book. Which which is in units of electron volts per Tesla. So then we get an answer of about 5.51 Teslas. And this is what the question refers to in the book.